Bien. ¿Dónde estamos? Hello, guys. Good evening. Thank you for coming on time. I'd like to say hi to every one of you guys. I had the opportunity to meet you at the exam. It's just two opportunities I have at the part. The first, the midterm exam, and the final exam. Yeah, that's the way it works for these virtual classes, just like this one. But I had the opportunity to meet, meet you all at once. But at least, I just saw you one. I just saw you one time in attendance, which was exam time. So I would like to say hi to the ones I see here. I'd like to say hi to Orlando, to Richard, to Sebastian, to Stephanie, to Juan Sebastian, to Talia, to Gabriela, to Luis Fernando, to Lady, to Carolina, and to Jenny. There's someone else in here. To Mateo. Okay, let's just say hi to every one of you guys. Let's go to what we have in our syllabus for the second half of the class. So let's share the syllabus. Before I do that, I have to make sure that the syllabus occupies the entire screen. Okay, good. So, okay, good. Okay, guys. So now, so far, up until here, up until the class before the midterm exam, we try to cover all this material. Yeah, two more people coming in. And so what we now have to make emphasis on, or the topics that we have to cover, are the ones you guys are seeing here right now, starting from process heat recovery. This is a very important topic because it has to deal with using waste energy, using energy from hot streams to exchange heat with cold streams, so that produces a savings in the pounds per hour of live steam required to heat up, some process streams. And we'll be hopefully dealing with that tonight and Thursday. So these 2 days we'll be dealing with that. Hopefully we'll cover that topic and then do a review on chemical reactors, move on with the economics of the process. Hopefully by now I have to contact Dr. Christopher Varela. He's going to give us a hand, help us with, so he's been helping us with a workshop, con un taller, a workshop for the use of the CapCost, the capital cost tool that Richard Turton developed. He developed a capital cost, a costing tool, a tool to help with the costing of an industrial plant, of a brand new chemical plant. And this tool is on Excel. So, and it's relatively simple to use. So Dr. Varela, he has prepared, a workshop, and he's been using his workshop with the students over the last 2 semesters. So hopefully, he has time, that would be great to have a workshop with him. I would say it might be between the 19, maybe the week of the 19, yeah, otherwise it would be the week of the 2nd of January. So one of these two, I have to ask Dr. Varela when he has some time to help us with that. Okay, so without further ado, we'll move on with process heat recovery. Quería hacer énfasis, ustedes ya habrán visto, todas sus notas están subidas en línea, así que, bueno, creo que con ustedes estamos completas con Andrea, que ha apoyado y ha apoyado, ¿no? Yo sé, de paso agradezco el apoyo de Andrea, su ayudante de cátedra, y estamos al día con ustedes. Creo que hasta ahora estamos al día. Muy bien, procedemos entonces a lo que nos toca el día, compartir el día de hoy. Okay, so there we are, process heat exchanger networks, which is la red de intercambiadores de calor. Justamente la recuperación de calor en una planta industrial tiene que ver con el tema de reaprovechamiento de calor y para ese fin utiliza una red de intercambiadores de calor. Vamos a ver qué consiste exactamente eso. Se nos ha atascado la barra aquí, una vez más. Quizá vamos a usar, este es el modo presentación, vamos a usar el modo no presentación hasta que la barra suba y ya podamos extender en modo presentación. Por alguna razón este computador ya tiene sus años y se atasca la barra por alguna razón. The analysis of the heat exchanger network first identifies sources of heat, termed as hot streams, and sinks, termed cold streams, from the material and energy balance. Consider first a very simple problem with just one hot stream and one cold stream. The initial, Melanie, the initial temperature, oops. Algo pasó con el PowerPoint. Algo pasó con nuestro PowerPoint. Esperamos que lo pueda recuperar pronto. ¿Dónde estamos? The initial temperature term supply temperature, final temperature term target temperature, and enthalpy change. Both streams are given in table 16. So we'll try to explain what it means the supply temperature, the target temperature, and the hot and cold streams. And that is hopefully in the next slide, if we can get to the next slide. Parece que el PowerPoint se está reiniciando por alguna razón. Se cayó el PowerPoint, se quedó congelado y el sistema lo está tratando de recuperar. Por lo que vamos a tener que tener un poquito de paciencia con este compu. Vamos a tratar de dejar de compartir y volver a compartir a ver si resuelve la situación. Vamos a ver. Ok. Vamos a ver acá. Creo que se puede compartir. Ups. ¿Dónde estamos? Ok. Viene Roger. ¿Dónde estamos? El PowerPoint. El PowerPoint desapareció. Ahora lo tenemos que abrir. Me disculpo que algo ocurrió con nuestro PowerPoint que simplemente se cerró. Entonces estamos abriéndolo de vuelta. Y ya nos vamos a conectar con nuestra diapositiva. Muy bien. Ok. Felizmente aquí está. Ok. Ahora procedemos a conectarnos con el PowerPoint. ¿Dónde está nuestro PowerPoint? Vamos a ver si lo encontramos. Y justamente. Listo. Por fin. Ok. Por fin. Y ahora sí nos podemos poner en nueva presentación. So the analysis of heat exchanger network first identifies sources of heat, term hot streams and sinks, term cold streams from the material and energy balance. Consider first a very simple problem with just one hot stream and one cold stream. The initial temperature terms supply temperature, final temperature term target temperature, and enthalpy change of both streams are given in table 16.1. So you could see here, the cold stream goes from low temperature or relatively low temperature to a higher temperature, while the hot stream goes from a hot temperature, 160 Celsius, to a cold temperature. And there is a delta, a change in enthalpy in megawatts, thermal megawatts, associated with the giving up of heat from the cold stream. And there is a required energy input. That's what you see it. I'm sorry, this is giving up heat from 160 to 40. So we have giving up heat to the environment. And this is a requirement of it. So we have to input 14 megawatts of heat for this stream. And while this stream is going to give up 12 megawatts of heat. So that's why you see how important it is to exchange heat from a stream that is giving up heat to a stream that is requiring heat, so that you don't have to unnecessarily use live steam from a boiler that is requiring bunker, which costs a certain amount of dollars per gallon. So if you can save that amount of money by exchanging heat between these two streams, that will be fantastic. Clearly, let's move this. It is possible to heat the cold stream using steam and cool the hot stream in table 16.1 using cooling water. However, this would incur in excessive energy cost. That is, instead of exchanging heat between this hot stream and this cold stream, just use live steam to heat this up and use cooling water from a cooling tower to cool this down. That will cost an enormous and unnecessary amount of money. It is also incompatible with the goals of sustainable industrial activity, which calls for use of the minimum energy consumption. Y eso es verdad, porque al final del camino, esto se traduce, digamos así, en dinero, en ahorro en dinero. Mientras usted más utilice vapor vivo, se le llama vapor vivo porque es vapor producto de quemar búnker o quemar gas natural en el caldero, lo cual cuesta por pie cúbico y tiene un valor, pie cúbico de gas natural, y tiene un valor, viene en estado gaseoso comprimido, ¿no? Y tiene un valor el búnker que en estado al ambiente sólido, por lo cual hay que estarlo calentando constantemente. Es un producto de una mezcla de hidrocarburos pesados, por eso al ambiente sólido para mantener los líquidos necesarios calentar el búnker. Pero tiene un costo por galón el búnker, y no solo eso, sino el quemarlo en el caldero arroja un montón de material particulado al ambiente. Entonces, no solo estamos ahí causando una ineficiencia en el uso de los recursos de la compañía al gastar innecesariamente dinero en servicios utilitarios como el vapor y el agua de torre, sino que estamos contaminando el ambiente innecesariamente. O sea, es doble error. Entonces, el uso del mínimo cantidad de energía necesaria, me refiero al vapor vivo del caldero, el consumo de agua de torre, porque todo esto cuesta, todo esto tiene un valor. Aunque a pesar que podría pensar, el agua de torre que está en la tina tiene que tener un tratamiento químico como el agua del caldero. Usted no va a hervir agua de la llave en el caldero, tiene que tener agua blanda para que no se incruste todos los tubos por fuera, ¿no? Que están en el caldero. Igual manera, el agua de la torre tiene que ser agua blanda para que no se le incruste la torre con magnesio y con calcio y con la dureza que normalmente tiene el agua, ¿no? Entonces, eso es muy importante. Este tema de ahorro de dinero y el mínimo uso de energía, solo lo estrictamente necesario. Instead, it is preferable to try to recover the heat between process streams, if this is possible. The scope of heat recovery can be determined by plotting both streams from table 16.1 on temperature enthalpy axis. For feasible heat exchange between the two streams, the hot stream must at all points be hotter than the cold stream. Figure 16.1, which is this thing, we'll go over this. By the way, we're going over the book of Robin Smith in 2005. So this discussion on process heat recovery will focus on Smith's approach and on Smith's method for dealing with process heat recovery. We're not going over Turton just because it is perhaps a simpler way to explain his reasoning and his logic for addressing this topic. That's why it's simple for us to understand and it's simple for us to convey, to share it with the public, with you guys. So we're studying this. As you can see this figure 16, that means this is chapter 16 from Robin Smith's book, which is Chemical Process Design and Integration. So figure 16.1a shows the temperature enthalpy plot for this problem with a minimum temperature difference of 10 degrees Celsius. Minimum temperature difference, that means minimum temperature difference between the hot streams and the cold stream. That is the difference in temperature between them, the minimum difference between the hot streams and the cold streams. That is the change. It will be the closest point between the two of them would be 10 degrees Celsius for this particular case. The region of overlap between the two streams in figure 16, Sophia, 16.1a determines the amount of heat recovery possible. For this problem, the heat recovery is 11 megawatts. So we'll go over that and we'll explain that carefully. the part of the cold stream that extends beyond the start of the hot stream in figure 16.1 cannot be heated by recovery and requires steam. So what are those comments addressing? Okay, so we can see here on the left, this is figure 16.1a, this is the A plot, and this is 16.1b. The difference between the two of them is here. The minimum temperature difference between this plot is 10 degrees Celsius, as you can see, between the hot stream and the cold stream is 10 degrees Celsius. While on the plot on the right, we see that the minimum temperature difference is 20 degrees Celsius. Okay, so how can we exchange heat between the two streams? We can exchange heat as long as they overlap. And as you can, they have a temperature overlap. And as you can see here, they do overlap between this point and this point. They do have this overlap, which will be equivalent between 160 and about 50 degrees Celsius. These two overlap, the hot stream and the cold stream. And since heat exchange flows from the hot stream to the cold stream, that is a natural way of flowing heat, then this stream, hot stream, could exchange heat with the cold stream if there is an exchanger, a heat exchanger between them. The region where they do not overlap is above 160 degrees Celsius, which is this region, will be the region to the right of the overlap region. So the overlap region is between this region that you can see here to the right of the overlap region where they do not overlap. That it requires a minimum amount of energy, which is this region, to fulfill the heating of this stream, because this stream is going from 40 to 110, but they cannot, they do not overlap in this region. So you need a minimum amount of energy for this stream to fulfill this duty of going from 40 all the way to 110. And that minimum amount of energy will be 3 megawatts. On the left of the overlap region, there is a minimum amount of cooling that is required, where the cold stream cannot be exchanged with the hot stream. I mean, the hot and the cold, they do not overlap, so there is no way to cool this hot stream down to the left of this overlap region, which is this small region right here to the left. And that requires 1 megawatt of cooling, and that will be done with a cooling tower. So in a process flow diagram, it will be expressed somewhat like what you're seeing here below the diagram, below this plot, this temperature enthalpy plot. Here you would have 160, you will have this hot stream coming in. You need to cool this down all the way to 40, and that's what you see in there. In between the cold stream, the hot stream, 160 going all the way to 40, you see in this strange exchanger, where on one side you see this line coming in at 40, which is equivalent to right there, the cold stream coming in at 40, and is exchanging heat with the hot stream, and then is requiring heat going all the way to 40 to 95, which is this point. And then there is a region where you have to input some live steam, which is you see right there. So it can go from 95 all the way to 110. Likewise, the cooling down of this hot stream from 160, it can cool down all the way to about 50. And then from 50 to 40, then you will need a cooling tower, which will absorb about 1 megawatt of energy. So this is approximately the way it would be dealt with in a process stream, where you will have an exchanger for heat recovery, which is this exchanger, and the minimum amount of live steam required for the process, which will be represented by this exchanger, and a minimum amount of cooling water required by the process, which will be represented by this exchanger. So far, so good. Then we'll study the next one in a few minutes, the next plot in a few minutes. This is a minimum hot utility of energy target, which for this problem is 3 megawatts. The part of the hot stream that extends beyond the start of the cold stream in figure 16.1 cannot be cooled down by heat recovery and requires cooling water, which is what we saw here. Here to the left, it requires cooling water. They do not overlap. You only had the hot stream coming from 50 to 40. And since the cold stream was going from 40 all the way to 110, having this a vertical line of minimum delta T beyond this to the left, then you require a minimum amount of energy to be absorbed by a cooling tower. And likewise here to the right, where they do not overlap, these two streams, they do not overlap. You require a minimum amount of energy as input into the process, as live steam that is coming from a boiler. This is the minimum cold utility, cold utility, which we saw to the left. Also shown at the bottom of figure 16.1a is the arrangement of heat exchangers corresponding with the temperature enthalpy plot, which is this arrangement which we saw in a few minutes ago. The temperatures or enthalpy change for the streams and their slope cannot be changed, but the relative position of the two streams can be changed by moving them horizontally relative to each other. This is possible, that is, we cannot change this slope, but we can move the streams. This one can be moved to the left or to the right. What happens if we move this to the left? If we move this to the left, then this delta T between, the closest region between the cold and hot stream will increase, just like you're seeing here on the right. By moving this to the left, then we have a bigger space between the cold and hot stream, but now delta T will not be 10. As you see in here, this is at 50, and the cold stream starts at 40, so delta T is 10. But now, if we move this to the left, then we'll have a bigger space between the two of them, which now is 20 degrees Celsius. So delta T minimum now is 20 degrees Celsius, and there are consequences for that as well. This is possible since there is moving the slope, maintaining the slopes of the two curves and moving them horizontally. It says this is possible since the reference enthalpy for the hot stream can be changed independently from the reference enthalpy for the cold stream. Figure 16.1b shows the same two streams move to a relative different position, such as delta T minimum now is 20, which is what we see right now. Because this stream with the exact slope was moved to the left. And when you move to the left, then you have a bigger space, and now it represents 20 degrees Celsius. But you are also seeing that it's requiring the region where they do not overlap, the hot and cold stream, they do not overlap. The region to the right represents now a bigger amount of energy that is needed as input. Instead of 3 megawatts, 4 megawatts are required. And also to the left of the region that they do not overlap, the two streams do not overlap. Now, you need to absorb 2 megawatts of energy with water from a cooling tower instead of 1 megawatt of energy. So there is like an equilibrium, if you may say that. So you're recovering, you're less strict in the heat recovery by having a delta T minimum of 20 instead of 10, but it comes with a price. That is, you need to input more live steam, more energy as live steam in the form of live steam, and you also will need to absorb more energy in the form of cooling water. So there is a price to pay for that. So what are you going to save if you have a delta T minimum of 20 instead of 10? What you will save in is in exchanges, in these exchanges, the exchanges for process heat recovery. So you have either you'll save in exchangers or you save in exchangers area. So the exchanger in here will have less heat transfer area than the exchanger in here, just because you're not recovering as much heat in this exchange as you are doing with this exchanger. The amount of overlap between the streams is reduced on the one of delta T minimum of 20, and hence the heat recovery is reduced to 10 megawatts. Yeah, that's what you see here on the right. The amount of recovery is just 10 instead of 11. So you're recovering less heat, that's why you have to input more heat, and now you have to absorb more excess, more waste in the form of cooling water, compared to what you did in the previous one, when you have a delta T minimum of 10. So there is a price to pay. You will recover just less energy, which will involve less area or less area in a heat exchanger, but you have to pay the price in more pounds per hour, let's just say, in live steam, and you have to pump so many gallons per minute of cooling water to absorb this. So there would be a price to pay in any case. Okay, I think we saw that. A greater amount of the cold stream now extends beyond the start of the hot stream, and hence the amount of steam is increased to 4 megawatts. Also, more of the hot stream extends beyond the start of the cold stream, increasing the cooling water demand to 2 megawatts. Thus, the approach of plotting a hot and cold stream on the same temperature enthalpy axis can determine hot and cold utility for a given value of delta T minimum. The importance of delta T minimum is that it sets the relative location of the hot and cold streams in this two-stream problem, and therefore the amount of heat recovered. Setting the value of delta T or QH minimum or QC minimum sets the relative location and amount of heat recovered. Consider now the extension of this approach to several hot streams and cold streams. Figure 16.2, 16.2, okay, shows a simple flow sheet. Flow rates, temperatures, and heat duties for each stream are shown. Two of the streams in figure 16.2 are sources of heat, or are called hot streams, and two are sinks, or heat, cold streams. Okay, very well. So now we're seeing this mole process is a simple flow sheet, and we are told that there are two hot streams and two cold streams. Very well, so let's identify the hot streams, and then let's identify the cold streams. So now we have numbered the different streams, so they're easy to check. Stream number 1 is going from 20 to 180, so this must be a cold stream. We also seen here that it's requiring 32 megawatts of energy input, so it's requiring a lot of energy input. Okay, stream number 2 is going from 250 to 40. So it's giving up 31.5 megawatts of energy. That is, you need that amount of energy to be absorbed by cooling water. That is, so you will need, a relatively big cooling tower for this service. Okay, stream number 3 is going from 140 to 230. So you need to input 27 megawatts of energy. That is an enormous amount of energy once again. So you can add 32 plus 27, it's like 60 megawatts or something like that, or 59. It's an enormous amount of energy that you're requiring just in two process streams. Stream number 4 is coming from 200 to 80. So it's giving up heat to the tune of minus 30 megawatts. So if you add minus 30 to minus 31.5, you have minus 61.5 megawatts that you need to absorb by using a cooling tower. So by now, your cooling tower has grown, and you need a humongous cooling tower to do this service. And also, you need a very big, or a series of boilers to produce the many pounds per hour of live steam at a given saturated pressure to achieve this, almost 60 megawatts of energy in the form of live steam to be input into the process. So this is going to be a very expensive process, to say the least. Assuming that heat capacities are constant, the data for the cold and hot streams can be extracted as given in table 16. So we'll explore that in a minute. Note that the heat capacities are total heat capacities, being the product of mass flow rate and specific heat capacity. So big CP is going to represent M times CP, as you will normally see in a heat exchanger, heat transfer, as you will normally see in a heat transfer type of problem. You will see mCp delta T, correct? Q is equal to mCp delta T, yes, as we know from heat transfer theory. But now to summarize, to shorten this and the use of mCp everywhere for this type of problems, big CP is going to represent mCp. Okay, so there's like the introduction of a new definition. So now we have the streams in here. You might remember the streams were 200 to 180, 250 to 40, 140 to 230, and 200 to 80, the 4 streams, the hot and cold streams. We'll see that in this table as well. We'll see the stream going from 20 to 180. That's a cold stream because it's requiring a heat input to go from 20 all the way to 180. So it was a cold stream. You might remember the stream number 2 was going from 250 to 40. So you need to give up an enormous amount of energy. Stream number 3 was going from 140 to 230. So you need to input energy once again. And stream number 4 was going from 200 to 80. So you need to, again, give up heat. Okay, so that represents these many megawatts, just like we saw in the process stream. And these are the heat capacities. Once again, big CP is equivalent to mCp. And M usually is in kilograms per second, or something like that, kilograms per hour, kilograms per second. And CP is kilojoules, kilogram Kelvin. So if you multiply both, you'll have this in megawatt per Kelvin. Why is that megawatt per Kelvin? Because if you multiply kilograms per second with kilojoules, kilogram Kelvin, the kilograms cancel out and you have kilojoules per second Kelvin. Kilojoules per second are kilowatts, thermal kilowatts per Kelvin. And that's what you see there. Now this is in terms of megawatts. So a million watts per degree Kelvin. This is pretty much what this represents. Okay, so far so good. We're listing the cold, hot streams, and we're also making, specifying the conditions of temperature of the different streams and the energy that they are either requiring as input or they're either giving up to be absorbed by the cooling water of a tower. And the heat capacity is representing mCp of each one of them. Instead of dealing with individual streams as given in table 16.1, an overview of the process is needed. Table 16.3a, which is this one, shows the 2 hot streams individually on temperature enthalpy axis. These 2 hot streams behave overall, can be quantified by combining them in the given temperature ranges. So we'll see how this arrangement is going to work out, and how the 2 individual streams the 2 individual hot streams can be combined into just one diagram. The temperature ranges in question are defined by changes in the overall rate of change of enthalpy with temperature. If heat capacities are constant, then changes will occur only when streams start or when streams finish. Okay, what does all this mean? So here on the left, what we're seeing, and also on the right, we're seeing the CPs. By the way, these CPs came from this diagram. So CP which is mCp of stream number 1 is 0.2, CP of stream number 2 is 0.15, CP of stream number 3 is 0.3, and it's 0.25 for stream number 4. So the 2 hot streams are going to be combined in one diagram, so you'll see the big CP of 0.15 and 0.25, and the 2 cold streams are going to later on be combined into one diagram, and they have 0.2 and 0.3. Okay, let's check how this works. So we have the 2 hot streams, 0.15 and 0.25, and they have a region of overlap where the temperatures overlap. The temperature of one stream coincides with the temperature of the other stream. The region where the 2 coincide is added up, that is 0.15 plus 0.25 is 0.40. So they're going to be combined into into one line, that is between here and here, the two slopes are going to be combined into one slope. And then the region where they do not overlap from 200 to 250, that's going to remain with a CP of 0.15, and the region below the region of overlap, which is this region right, is also going to remain with the same slope with a CP of 0.15, just like you see there. Once again, this is for the hot streams. It says in here, the hot streams can be combined to obtain a composite stream, which is this stream. Now, instead of requiring 31.5 and 30 megawatts individually, once you combine them, the two of them, instead of requiring about 59 megawatts, they only require 48 megawatts now, which makes sense. And there is a region where they do not overlap, which is the one 7.5 to the right and 6 megawatts to the left. Okay, so far so good. And the span of the required amount of total amount of energy required 61.5 for the two of them. Oops, let's move this around. Combination of the two hot streams. Está Puerto Limpio acá afuera. Usualmente se toma solo unos pocos minutos. Entonces, in figure 16.3, the temperature axis, say 16.3, there you go. Temperature axis is divided into ranges defined by the supply and target temperatures of the streams. Within each temperature range, the streams are combined to produce a composite hot stream. This composite hot stream has a CP in any temperature range that is the sum of the individual streams. As you see there, this is the sum of these two individual streams as long as they overlap. In this region of temperature where they overlap, you can add them up and then you have a new slope as a result of the addition of the two CPs. Within each temperature range, the streams are combined to produce a composite hot stream. This composite hot stream has a CP in any range, in any temperature range, that is the sum of the individual streams. Also, in any temperature range, the enthalpy change of the composite stream is the sum of the enthalpy changes of the individual streams. Figure 16.3b, which is the one we saw right there, 16.3b, shows a composite curve of the hot streams. The composite hot stream is a single stream that is equivalent to an individual hot streams in terms of the temperature and enthalpy. Similarly, the composite curve of the cold streams, now we have the cold streams right there. Two cold streams where they're in with their individual CPs are right there. They are shown in figure 16.4. Again, the composite cold stream is a single stream that is equivalent to the individual cold streams in terms of temperature and enthalpy. So now we do the same process like we did with the hot streams. And we are careful to observe why the two cold streams, they cross each other. And they cross each other between 140 and 180. So these two CPs can be added within this small range. 0.2 plus 0.3 will be 0.5 in this small range, as you can see right there. So below 140, the slope is kept and the CP is kept the same. And above 180, the slope is kept and the CP is kept the same, just like you see right there. So the CP of 0.5 is added only in the region where the two cold streams cross each other, which is this stream right there. They demand what they're giving up. The 59 megawatts of energy needs to be absorbed in total, and it's the same amount of energy that needs to be absorbed. But the region where they are combined is only 20. There you go. And this is a combination of the two cold streams right there. The composite hot and cold curves can now be plotted on the same axis as in figure 16.5. So now what has been done is taking this combined cold composite curve and the combined hot composite curve and putting one right next or one on top of the other. So this hot composite curve is going to be placed on the same axis on top of the cold composite curve. We're going to see that right there in this plot. Let's just read what it mentions in here. Plotting the composite hot and cold curve is analogous to plotting the single hot and cold streams in figure 16.1. The composite curves in figure 16.5a are said to have a minimum temperature difference of 10 degrees Celsius, where the curves overlap in figure 16.5a. Heat cannot be recovered vertically from the hot streams that comprise a hot composite curve into the cold streams that comprise the cold composite curve. So what does that mean? Okay, so we have a minimum temperature difference that is the closest point between the hot composite curve and the cold composite curve. The minimum difference in temperature between the two of them is 10 degrees Celsius. Okay. So when we place this composite curve on top of each other, then there is a region where they do overlap. Where the hot composite curve starts is one of the regions of overlap, and the limit is where the cold composite curve overlaps with the hot composite curve. So beyond this, to the left of this is a minimum amount of energy that needs to be absorbed from the system. And to the right of this is a minimum amount of energy that needs to be input into the system. And it comes out to be 7.5 megawatts, the minimum amount of input energy, and 10 megawatts, the minimum amount of energy that needs to be absorbed from the process. Okay, so far, so good. This is from 10 degrees Celsius. If we move this hot composite curve to the left, making this space a bigger space, then we can have a difference of 20 instead of 10. But as you will notice, the minimum amount of energy required will be bigger, as you see here, 11.5 instead of 7.5. And the amount of energy that needs to be absorbed now instead of 10 is 14. So as I mentioned, and the recovery, the energy being recovered instead of being 51.5 megawatts, now is just 47. So there is a price to pay. We can recover. If you want to do that, invest less in regenerating type of heat exchangers, invest less in additional heat exchangers to exchange heat between hot and cold streams. We can do that and save some money. But at the end of the day, we're going to pay the price for that. That is, we're going to be requiring more live steam, more energy in the form of live steam. And we're going to be requiring more gallons per minute of cooling water to be able to absorb a bigger amount of energy, waste energy from the system. So there's a price to pay when we recover less energy. Pretty much that's what it is. What we also see here, okay, so we see, we're just pointing out the amount of energy being recovered, the amount of energy, additional energy as input. Diego. Oops. Okay, additional energy as input and the minimum amount of energy to be absorbed from the system. So it's just making an emphasis of that. The way in which the composite curves are constructed, monotonically decreasing hot composite curve and monotonically increasing cold composite curve. What is meant by monotonically? You see this curve coming from with different slopes, but it's just one continuous, let's just say a continuous line, a composite line describing the hot stream, and one continuous cold composite line describing the cold stream. That's what it means by monotonically. So the way in which the composite curves are constructed allows maximum overlap between the curves and hence maximum heat recovery, which is what we're seeing. What we're seeing there is a maximum heat recovery by having this minimum temperature difference between the hot and cold composite curves. Maximizing the energy recovered thereby minimizes their external requirements for heating and cooling duties and minimizes the energy consumption. In this problem, for delta T minimum of 10 degrees Celsius, the maximum heat recovery is 51.5 megawatts, just like we see right there. because there is a minimum difference of only 10 degrees Celsius. We also mentioned that in this case, we were recovering less heat because the minimum difference between the hot and cold composite curves was twice the amount of the first case, which is 20 instead of 10. Where the cold composite curve extends beyond the start of the hot composite curve in figure 16.5a, heat recovery is not possible, and the cold composite must be supplied with external hot utility, such as steam, which is what we saw there. Yeah. Beyond this, beyond the start of the hot composite curve, where energy cannot be exchanged between the hot and cold stream, then you need just live steam right there. Additional steam needed, a minimum amount of energy required, in addition to the heat recovery. This represents a target hot utility. For this problem, it was 7.5 megawatts for delta T minimum of 10. Where the hot composite curve starts beyond the start of the cold composite curve, heat recovery is again not possible, and the hot composite curve must be supplied with external cold utilities, such as cooling water. This represents a target for cold utility, and for this problem, it was a QC minimum of 10 megawatts, which is what we see right there to the left, where they do not overlap each other. Then you need to absorb this excess heat or this waste heat from the process. Let's just say waste heat from the process, and that will need to be absorbed in the form of cooling water. Okay, so far so good. Specifying the hot utility or cold utility, heat duty, or delta T minimum fixes the relative position of the two curves. As with simple problem in figure 16.1, the relative position of the two curves is a degree of freedom. Again, the relative position of the two curves can be changed by moving them horizontally relative to each other. And that's what we see here when we move this hot composite curve to the left and we fix the position of the cold composite curve, then eventually there will be a bigger space between the two of them, but that bigger space will come at a price. Yes, we will need less capital investment in heat exchangers and less capital investment in heat exchanger area, but there will be a price to pay in the amount of minimum energy required as input into the process, and there will be a price to pay in the amount of energy that will need to be absorbed from the waste heat coming from the process. Just like you see here, the QH minimum is bigger than the QH minimum that the process required with delta T minimum of 10. And also the waste energy, instead of being 10, now is 14. So there is a price to pay when we do this. So, okay. Clearly, to consider the heat recovery from hot streams into cold streams, the hot composite curve must be in a position such that it is always above the cold composite curve for a feasible heat transfer. Thereafter, the relative position of the two curves can be chosen. Figure B, 16.5p, shows a curve with a delta T minimum of 20. The hot and cold utility targets are now increased to 11.5 for QH minimum and 14 megawatts for QC minimum. These are respectively. This is 11.5 QH minimum and 14 QC minimum, just like we see right there. 14 is for QC minimum, 11.5 is QH minimum right there. So just like we mentioned, it increased. It increased because delta T minimum now is bigger. Okay. So now we're focusing on the diagram on the right, and we're seeing that the maximum heat recovery has decreased from 51.5 to 47.5. We see that we're requiring a bigger QC minimum than before, and also a bigger QH minimum than before. We also identify the hot composite curve and the cold composite curve, and we have a bigger delta T minimum than before. Pretty much what we were discussing. Figure 16.6, which is now this figure, illustrates what happens to the cost of the system as a relative position of the composite curve is changed over a range of values of delta T minimum. When the curves just touch, there is no driving force for heat transfer at one point in the process, which will require infinite heat transfer area and hence infinite capital cost. That is, if these two, let's say the hot composite curve and the cold composite curve, they would touch. For that to be feasible, you need a heat transfer area of infinity, pretty much, and so that you will have exact same temperature between the two of them, which is nearly impossible. In real life, it's nearly impossible. For the first condition, you see the second condition, there is a bigger space between the two of them. And for the first condition, there is a, smaller space between the two of them. So the cost, you could see the cost for the first condition is going to be higher. The total cost is going to be higher. Not only for total cost, but for the capital cost, that is the investment to achieve this will require either more exchangers or more heat transfer area. In any case, it will be a higher capital investment to achieve this, a greater heat recovery. For this one, where you're not so strict in the amount of energy recovered, should be in a second position. So there will be a balance between the capital cost, you see it's requiring now less capital cost right there. And or let's just say less total cost than the one on the first position, the one we just saw. The total cost will be just higher, while the total cost in here will be just lower. So according to what we see, this simple plot is telling us that we have to eventually reach an economic optimum. That we don't have to necessarily be so very strict as to require a huge investment, but we can reach an optimum where just enough, enough exchangers and enough area would just be the optimum, just like we see right there. The energy cost will increase if we have less heat transfer area. The energy cost will increase just like you see there, but the capital cost will decrease. So there is a balance between the two of them. At the end of the day, if we consider the capital investment and the energy investment, the energy cost, there will be a total cost. And that total cost still will be lower than if we just focus on having the maximum energy recovery with the minimum amount of energy. But the investment in the capital investment will erase any savings, let's just say, any savings in energy we might have. So ideally, it will be good to just reach an optimum and not just aim for the most strict, let's just say, the most strict and the lowest delta T minimum. As an energy target, and hence delta T minimum between the curves is increased, the capital cost decreases. Yeah, as you see there, as you have these delta T increases, let's just say from 10, it goes to 20, it goes to 30. As it increases, then the capital cost decreases, just like you see right there. This results from increased temperature difference throughout the process, decreasing the heat transfer area. On the other hand, the energy cost increases as delta T minimum increases, just like you see there. The capital cost decreases, but the energy cost increases. Energy cost in live steam and in cooling water, that will increase. On the other hand, there is a trade-off, un balance se podría decir. Trade-off es como un intercambio. There is a trade-off between energy and capital cost and an economic amount of energy recovery. Later, it will be shown how this trade-off can be carried out using energy and capital cost targets. Este balance, este intercambio, eventualmente uno buscaría que llegue a un equilibrio, ¿no? However, care should be taken not to ignore practical constraints when setting delta T minimum. To achieve a small delta T minimum in a design requires heat exchangers that exhibit pure countercurrent flow. Es importante esto. No sé si alguien en el examen me preguntaba el problema de intercambiadores de calor si podíamos asumir flujo a contracorriente. Y efectivamente así es. Porque a contracorriente se espera que sea un sistema más eficiente. Entonces, usted ve que justamente es lo que se considera para los procesos de recuperación de calor. Que los intercambiadores funcionen a contracorriente, como lo especifica aquí. Pure countercurrent flow. With shell and tube heat exchangers, this is not possible, even if a single shell pass and single tube pass designs are used, because the shell size teams takes periodic cross flow. Consequently, operating with delta T minimum less than 10 should be avoided unless under special circumstances. Entonces nos dice que ustedes se habrán fijado cuando vimos en discusión de intercambiadores de calor, que un intercambiador de tubo y carcasa que tiene dos pasos, en un paso va a estar concurrente con el vapor, porque el vapor va al lado de la carcasa, y en el siguiente paso va a estar contracorriente con el vapor, es decir, no es un intercambiador a contracorriente puro, tiene parte de su flujo es a contracorriente, parte de su flujo es concurrente. Ese tipo de arreglos funciona bien con intercambiadores de placa, porque en una placa efectivamente usted puede tener el flujo de un lado y el otro flujo del otro lado, y eso nunca va a ser concurrente, sino usted lo puede tener contracorriente puro siempre en un intercambiador de placas. Intercambiador de tubo y carcasas no, porque el flujo va, luego el flujo regresa, si es de dos pasos, si es de cuatro pasos va y regresa, y a menos de que sea de un solo paso, donde el flujo del líquido a calentar o enfriar va de izquierda a derecha y el fluido del vapor va de derecha a izquierda, pero como hay baffles entre medio, entonces los baffles va haciendo que cambie la dirección del fluido por fuera de los tubos, entonces no es tan, digamos así, no es tan puro, no es tan puro la contracorriente de un flujo con el otro, sino ese tipo de intercambio. Tubo de carcasa no funciona así como algo, digamos, puro, sino sería de pronto otro tipo de intercambiador más preciso, como sugería el de placas. Ujú. A smaller value of 5 degrees Celsius or less, o sea, un delta T minimum of 5 or less, can be achieved with plate heat exchange. Una vez más, ahí están los intercambiadores de placas. Esos son más eficientes en lograr un delta T mínimo en la curva compuesta caliente y la curva compuesta fría de 5 grados, que sería bastante estricto. Dicho sea, requeriría una cantidad de inversión en área de transferencia enorme para lograr algo así. And can be, and the value can go as low as 1 to 2 degrees Celsius with plate thin design. O sea, un diseño especial que tenga fin design, que tenga aletas, un intercambio de placas con aletas, puede llegar a un valor de delta T mínimo de 1 grado, una cosa impresionante, ¿no? It should be noted, however, that such constraints only apply to the exchangers that operate around the point of closest approach between the composite pores. Additional constraints apply if vaporization or condensation is occurring at the point of closest approach. Okay. Hay unas consideraciones especiales en el caso de que está ocurriendo una condensación o vaporización en el punto más cercano de delta T mínimo, entre la curva compuesta caliente y la curva compuesta fría. The heat recovery pinch. As discussed above, the correct setting of the composite curve is determined by an economic trade-off between energy and capital, corresponding to an economic minimum temperature difference between the curves. Accepting for the moment that the correct economic delta T is known, it fixes the relative position of the composite curves and hence the energy target. Por lo pronto, y para efectos de esta clase, vamos a asumir que el delta T min nos ha sido dado y así pues proceder en la resolución de los ejercicios, ¿no? No vamos a calcular el delta T óptimo para efectos de esta clase, ¿no? Porque lo que estamos haciendo es una revisión de temas importantes de proceso, por lo cual nos vamos a centrar en justamente eso. Y vamos a hacer pues cierta suposición. El libro las hace, el libro de Smith las hace, que el valor de delta T mínimo ya nos es dado de por sí. The value of delta T minimum, propósito usted verá pues citas aquí al pie de la diapositiva y son las citas del autor porque estos métodos que el autor está citando pues fueron desarrollados por otros investigadores en diferentes tiempos. Entonces el autor ha recogido esta investigación de otros autores, de otros investigadores y las ha publicado en su libro, ¿no? Pero él le da el crédito a quien corresponde, ¿no? Así como ocurre con el doctor Linhoff, Umeda, y en fin, todos los demás investigadores, ya sean japoneses, norteamericanos, que usted, o de diferentes países, ¿no? También hay rusos, etcétera, o asiáticos que se ven a lo largo de esta clase, porque hay un montón de investigadores que son citados en diferentes tiempos. Quién sabe si alguno de ellos estarán vivos o ya no estén vivos, ¿no? Como el doctor Sider and Tate, de la correlación Sider and Tate que vimos hace un momento, Ditus and Bolter, que son correlaciones ya tienen sus décadas. Pero en fin, estas están siendo citados por el autor y por eso aparecen todas estas citas al final de la diapositiva, ¿no? Entonces vemos heat recovery pinch, the value of delta T minimum and its location between the composite curve have important implications for design. If the energy target is to be achieved in the design of a heat exchanger network, the delta T minimum is normally observed at only one point between the hot and composite curves called the heat recovery pinch. The pinch point has a special significance. El punto pinch, ya lo vamos a estudiar, lo vamos a observar en gráficos con cuidado. The trade-off between energy and capital in the composite curve suggests that, on average, individual exchangers should have a temperature difference no smaller than delta T minimum. A good initialization in heat exchanger network design is to assume that no individual heat exchanger has a temperature difference smaller than the delta T minimum between the composite curves. Correct. With this rule in mind, divide the process at the pinch point as shown in figure 16.7a. Vamos a ver con cuidado. Above the pinch, in temperature terms, the process is in heat balance with the minimum hot utility, QH minimum. Heat is received from the hot utility and no heat is rejected. The process acts as a heat sink. Claro. Sobre el punto pinch, estamos recibiendo energía asumimos del caldero, ¿no? En la manera de vapor saturado. Y esa energía que estamos recibiendo por la condensación del vapor saturado no está siendo rechazada, sino que está siendo usada por el proceso para calentar líneas de proceso. Entonces el proceso está actuando como un, ¿cómo se diría? Un absorbedor de energía, se le llama heat sink. Below the pinch in temperature terms, the process is in heat balance with the minimum cold utility, QC minimum. No heat is received, but heat is rejected to cold utility. The process acts as a heat source. Claro. Por debajo del punto pinch, por debajo de ese punto donde está el delta T mínimo, donde se rechaza ya calor, donde hay energía en exceso que se rechaza del proceso y es absorbida por el agua de torre, el proceso está actuando como una fuente de energía porque está proveyendo constantemente energía desperdicia, este exceso de energía que necesita ser absorbido por el agua, del sistema de enfriamiento del agua de torre, ¿no? El proceso en ese punto se convierte en un proveedor de energía, en una fuente de energía. Se observa en este diagrama. So here we see a delta T minimum of 10 degrees Celsius. Saying how heat transfer from above the pinch to below the pinch is possible. This is the pinch right there. The pinch identifies the place where we have a minimum delta T. So above the pinch can exchange heat with a point below the pinch. But what cannot be possible is to go from below the pinch and to exchange heat to a point above the pinch. So you see here, we're going from 185 to 95. You can exchange heat. This 195 in the hot composite curve can exchange heat with this cold stream that has 95 degrees Celsius. So you can exchange heat in here. This is feasible. But here, going from 120 in the hot composite curve to 165 in the cold composite curve, this is just impossible. This is not possible. Heat transfer from below to above the pinch is not possible without violating delta T minimum. Also, we could see how the process acts as a heat sink above the pinch, where we are requiring a minimum amount of energy, and how this is the pinch, and how the process is acting as a heat source below the pinch, where heat is rejected. And there is a minimum amount that needs to be absorbed by a cooling tower provided. Consider now the possibility of transferring heat between the two systems. Figure 16.7b shows that it is possible. 16.7b, there you go. It is possible to transfer heat from hot streams above the pinch to cold streams below it, just like we see here. This is the pinch, this is above the pinch, this is below the pinch. So this is possible to exchange heat from above the pinch to below the pinch. The pinch temperature for the hot streams for the problem is 150, and the cold streams are 140. Transfer of heat from above the pinch to below, as shown in figure 16.7, means transfer of heat from hot stream with a temperature of 150 or greater into cold streams with a temperature of 140 or less, which is what we see here. We're transferring heat from a stream of 185, which is above the pinch, above 150, to below 140, to a stream below 140, which is at 95. So this is possible. By contrast, figure 16.7c shows that heat transfer from hot stream below the pinch to cold streams above is not possible, which is what we see there. We are at the hot composite curve, 120, so we're at a temperature below the pinch. Remember, the pinch is between 150 and 140. So 150 will be on the side of the hot composite curve, and 140 will be on the side of the cold composite curve. So in a natural way, we'll have to be above the pinch. We'll have to be above 150 to exchange heat with the stream below 140. That would make sense. But we are now below 140, we're at 120, and we cannot exchange heat with the stream above the pinch, above 150, which is now 165. This is not feasible. Physically, this is not possible, which is what we're seeing here. Such transfer requires heat being transferred from hot streams with a temperature of 150 Celsius or less into cold streams with a temperature of 150 or greater. This is clearly not possible without violating delta T minimum constraints. If an amount of heat, Xp, is transferred from the system above the pinch to the system below the pinch, as in figure 16a, this will create a deficit of heat above the pinch and an additional surplus of heat below the pinch. The only way this can be corrected is by importing an extra Xp amount of heat from a hot utility and exporting an extra Xp amount of heat to cold utility. Once again, heat is expressed as Xp in this diagram. So we see that QH minimum plus an additional an amount of energy going from above the pinch to a process side above the pinch. So this is acting as a heat sink. Is exchanging heat with a part of the process below the pinch. So this part of the process below the pinch is acting as a heat source, because it's going to be rejecting heat eventually out of the system and will need to be absorbed by a cooling tower. So if we add additional heat to the QH minimum, that additional heat will cascade down all the way to the excess waste that will need to be absorbed. So we input heat here, that is going to cascade down all the way down here, which is the same amount will need to be retrieved from the process, will need to be absorbed. This additional amount will need to have additional cooling tower, megawatts in capacity to absorb this additional amount of energy that was input up here. Analogous effects are caused by inappropriate use of utilities. Utilities are appropriate if they are necessary to satisfy the enthalpy imbalance in that part of the process. Above the pinch, hot utility, in this case steam, hemos hablado de vapor vivo, ¿no? Porque es la manera más barata de usar la energía en un proceso, es vapor, ¿no? Vapor saturado. Above the pinch, hot utility is needed to satisfy the enthalpy imbalance. Figure 16.8b, okay, illustrates what happens if inappropriate use of utilities is made. So in this case, we're seeing that we have a minimum requirement of QH minimum, and an excess of energy is being input into the process, but there is a waste. There is a deviation of the energy. That excess energy is going, is going to the ambient. It's not cascading down to the part of the process below the pinch. So there is some sort of interruption between the heat sink part of the process above the pinch and the heat source part of the process below the pinch. There's some sort of interruption. So energy is not cascading down naturally. Probably there are no heat exchanges between the two of them, between the heat sink and the heat source. There are no heat exchanges. So we're just wasting energy. This is a clear way to waste energy. Okay. If cooling to cold utility XP is used to cool hot streams above the pinch, this creates an enthalpy imbalance of the system above the pinch. To satisfy the enthalpy imbalance above the pinch, an import of QH plus XP heat from hot utility is required. Overall, QC minimum plus XP of cold utility is used. So that's what we saw in here. If we input an additional amount of energy, that's going to cascade down all the way, pretty much all the way to the medium that is going to absorb the heat, which is the cooling water. That would need to be absorbing this extra amount of energy that was inputted here. Another inappropriate use of utilities involves heating of some of the cold streams below the pinch by hot utility. Below the pinch, hot utility is needed to satisfy the enthalpy imbalance. Figure 16.8c illustrates what happens if an amount of heat from hot utility is used below the pinch. QH minimum must still be supplied above the pinch to satisfy the enthalpy imbalance above the pinch. See, what is happening here, that instead of this additional amount of energy being input into the process that is acting above the pinch as a heat sink, if you input here the part of the process that is below the pinch, where it's actually acting as a heat source, you're just wasting energy again, because this part of the process below the pinch is giving up heat. So if you input heat to a part of the process that's giving out heat, you're just wasting energy and wasting money. This is completely unnecessary. Just like this part is just completely unnecessary. You're wasting energy. There is no natural cascade between the heat sink and the heat source. So energy is going somewhere. Maybe it's going to the ambient. So you have a whole, all these hot pipes around the process, exchanging heat nowhere. You're just wasting energy. It's a good way to waste money. So overall, QH minimum plus XP of steam is used and QC minimum plus XP of cooling water. In other words, to achieve the energy targets set by composite curve, the designer must not transfer heat across the pinch by process-to-process heat transfer or by inappropriate use of utilities. These rules are both necessary and sufficient to ensure that the target is achieved, providing that the initialization rule is adhered to, that no individual heat exchanger should have a temperature difference smaller than delta T. So once delta T was fixed between these two, between the hot composite or the part of the process is acting as a heat sink and the part of the process acting as a heat source, this delta T minimum in here, once that is fixed, then no exchanger will have a delta T minimum below that. So if it was expressed, a delta T minimum was going to have 10 degrees Celsius temperature difference, then all the exchangers will have that difference or above. They will not have that difference or below. So that would need to be respected. Okay. Figure 16.9a, we're right there. This is 16.2 and this is 16.9. Figure 16.9a shows a design corresponding to the flow sheet of figure 16.2, which achieve the target QH minimum of 7.5 and QC minimum of 10 megawatts for delta T minimum 10 degrees Celsius. So you might remember this that we previously saw, very inefficient process that we had these 4 streams. Some were hot, just like, let's say, this was a hot stream and this was a hot stream, and some were cold. This is a cold stream and this is a cold stream. But they were very inefficient because you were requiring 59 megawatts in here, and you were requiring above 61.5 megawatts to give up of it. So an enormous amount of energy, either as input or as energy waste from the process. But figure 16.9 now has the same process. But the same process, now you see many more exchangers that are used for the process heat recovery. You will find that previously we had all these exchangers for live steam. So 1, 2, they were used for live steam to heat this up, live steam, and these 2 exchangers were used for the cold utility, like for cooling water. So you have 4, 2 for live steam, heating up of the process streams, and 2 for cooling water to cool down the process streams. But now, in this design, you only have 1 exchanger to be used for the hot utility, to be used for the steam, for live steam, and one exchanger to be used for the cold utility. So it's a more efficient use of the utility services of an industrial plant. And you're also saving a lot of money in doing that. So you see that instead of requiring 69 megawatts of energy and having no heat recovery whatsoever, here you only requiring 7.5 megawatts of energy. So if we divide 7.5 by 69, you have an idea how much you're saving in energy. You're only requiring about 11% of the energy that you were requiring before. And now you only need to absorb 10 megawatts instead of 61.5 megawatts between the 2 of them. So if you divide 10 by 61.5, now you're only requiring 16% of what you were requiring in this non-efficient process. But you also seen that there is an additional amount of exchangers that you are requiring for this process heat recovery between hot streams and cold streams. And you have 1, 2, 3, 4, 5, 6 additional exchangers to the exchanger using hot utility and the cold utility. So you have, in total, you need 8 exchangers instead of 4. So there is an additional amount of energy, additional amount of money that will need to be invested in capital, invested as capital investment in heat exchangers with the required heat transfer area, and the piping, the valves, the control system. So there will be some cost. So definitely there will be some cost. But at the end of the day, that cost will represent savings in the process. Long term, it will represent savings. Figure 16.9b, let's say this is, where is 16.9b? This is 16.9b. Okay, so this is 16.9a. There you go, 16.9a. Figure 16.9b shows an alternative representation of the flow sheet in figure 16.9a, known as a grid diagram. Preste atención que este es un diagrama de flujo optimizado, donde tenemos intercambiadores de calor para líneas de proceso calientes y frías, adicional al intercambiador que usa vapor vivo, en este caso, y el intercambiador que está usando agua de torre, que es en este caso. Los demás son intercambiadores regeneradores, se les dice en la vida real, se les dice regeneradores, porque está tomando de la línea caliente de proceso, intercambiando ese calor que ya de por sí viene de la línea caliente de proceso con una línea fría que va a proceso. Entonces se le llama regeneradores. Y se deja la definición de intercambiador de calor para aquellos que efectivamente, a pesar que todos son intercambiadores de calor, pero el que está usando vapor vivo El que está usando agua de torre, pues son los intercambiadores de calor propiamente. Y los que están regenerando calor se les llama también regeneradores, como el caso de estos 4, 5, 5 no, 2, 3, 4, 5, correcto, 5. Y el que usa vapor y el que usa agua de torre son 2 más, son 7, pero pensé que eran 8, son 7 en realidad. Esto se puede expresar como está en este diagrama de líneas. Y esto se lo llama grid diagram. Es importante porque si llego a preguntar esto en un examen, ustedes tienen que saber qué es un grid diagram. Y el grid diagram, como lo expresa aquí, acá está. Figure 16.9b shows an alternative representation of the flow sheet in Figure 16.9a. Una vez más, este es el 16.9a. A, según, como usted puede ver ahí, A, según la figura 16.9 del libro de Turton, capítulo 16. Pero representar esto como está es un poco complicado, como usted lo puede ver aquí. Las líneas están cruzadas la una con la otra, como aquí un cruce de líneas y ahí la línea sale, en este caso el reactor va, un regenerador regresa, otro regenerador, a un tercer regenerador va al intercambiador. Es decir, es complicado. Es más fácil ilustrarlo en este modo. Y vamos a ir con cuidado explicando el grid time. ¿Cómo diríamos grid? En español no estoy exactamente seguro. Pero si llego a mencionar el grid diagram en el examen, tienen que ustedes enfocarse que me estoy refiriendo a este tipo de dibujos. Es un dibujo simple, donde se ilustran con claridad las líneas calientes, las líneas frías y cómo intercambia el calor la una con la otra. Este tipo de dibujo, así no les voy a pedir un diagrama porque esto es complicado. Será conveniente, en mi humilde opinión, pedir esto en un examen donde ustedes tienen un tiempo medido. Pero este tipo de dibujo es más accesible, más simple y es cuestión de manejar los conceptos con claridad para poder graficar algo así. Una vez más, esto es un grid diagram. Como se menciona aquí, grid diagram. The grid diagram shows only heat transfer operations. Hot streams are at the top, running left to right. Aquí podemos ver left to right are the hot streams. They are at the top. Las líneas calientes van en la parte superior de este diagrama del grid, diagrama de entramado, no sé exactamente cómo llamarlo, pero se dan prioridades. Izquierda a derecha van las líneas calientes, derecha a izquierda van las líneas frías. Líneas calientes porque tienen una alta temperatura y van a una temperatura más baja, como pueden ver en líneas 2 y 4. Y líneas frías porque van de una relativa baja temperatura. Digo relativa porque está a 140, no es exactamente baja, pero va de esta temperatura a una temperatura superior. Entonces, este de aquí es una línea que en teoría, en comillas, se le diría fría, ¿no? En realidad está bastante caliente, pero se le diría fría, relativamente fría, porque está ganando energía en lugar de perdiendo energía como esta de acá. Y esta va de 20 a 180. ¿Qué más nos dice? Cold streams are at the bottom, running left to right, right to left. A heat exchange match is represented by a vertical line joining two circles on the two streams being matched. An exchanger using hot utility is represented by a circle with an H. Entonces aquí vemos match. Este es la línea que está usando el intercambiador con vapor vivo, el H. Y es la línea que está usando el intercambiador con agua de torre, C, cooling water, que se le dice al agua de torre, C. Las demás líneas que cruzan entre sí con estos círculos grandes son lo que se dice líneas que se han intercambiado calor. Y luego vamos a ir explicando con detalle este intercambio de calor y cómo proceder un análisis de este tipo. An exchanger using cold utility is represented by a circle with a C. The importance of the grid diagram is clear in figure 16.9b since the pinch and how it divides the process into two parts is easily accommodated. Entonces aquí tenemos el pinch que estaba entre 140 y 150 y vemos, divide el proceso en dos y vemos como la temperatura sobre la temperatura caliente del pinch, que es 150, es separada la temperatura fría del pinch, que es 140. Recordemos que el pinch en este proceso en particular estaba entre 140 y 150. 150 grados centígrados vendría a estar del lado del hot pinch, como le digo, del lado de las líneas calientes, y 140 grados centígrados vendría a estar del lado del cold pinch, o de las líneas frías. Por eso usted ve expresado cuando el proceso se divide en dos, en la parte caliente del pinch de 150 se ubica aquí y se expresa aquí en este diagrama de entramado, como lo podemos, no sé cómo expresarlo. Y la parte fría del pinch, las líneas a 140 se expresan en las líneas inferiores y en las líneas frías. ¿Qué más vimos aquí? Dividing the process into two parts on a conventional diagram such as shown in figure 16.9a is both difficult and extremely cumbersome. Si ponernos a hacer algo así en imagínense, bueno, en una tarea sería suficientemente complicado para hacerlo en un examen, sería una cosa tremenda, bastante complicada. Y probablemente la absorbería una barbaridad de tiempo y sería sujeto a cometer muchos errores, ¿no? Nos vamos a centrar más bien en este aspecto de la regeneración de calor. Aquí usted puede ver las líneas de proceso en todo este entramado de líneas como un PFD, ¿no? Pero es bastante complicado, como lo podemos ver. For now, simply take note that the targets set by the composite curves are achievable in design, provided that the pinch is recognized and there is no transfer of heat across a pinch, either process to process or through inappropriate use of utilities. However, the insight of the pinch is needed to analyze some of the important decisions still to be made before the network design is addressed. Although composite curves can be used to set energy targets, they are inconvenient since they are based on graphical construction. Entonces, ponernos a hacer un gráfico de la curva compuesta caliente y fría, se la puede realizar, pero cuando ya hay varias líneas de proceso se vuelve un poco, no sé si decir, obviamente se va a complicar la cosa. Decimos, se va a un poco peluda la cosa, ¿no? Se va a complicar la cosa. A method of calculating energy targets directly without the necessity of graphical construction can be developed. The process is first divided into temperature intervals in the same way as was done for construction of the composite curves. Esta es una manera de hacer, de utilizar los datos que podría obtenerse de un diagrama compuesto de líneas calientes y frías, pero a manera de tabla. Es bastante más sencillo. Y esto se llama el algoritmo del problema de la tabla. Problem Table Algorithm. The process is first divided into temperature intervals in the same way as was done for construction of the composite curves. Figure 16.14a shows that it is not possible to recover all of the heat in each temperature interval since temperature driving forces are not feasible throughout the interval. Veamos si tenemos. Acá está. Nos dice, aquí podemos. Lo que nos dice es que en la vida real, recuperar calor entre la línea caliente y la línea fría, todo este calor que vendría a representar esta diferencia de temperatura en la vida real, no es posible. Lo que es más accesible es si tenemos una representación así de lo que realmente puede recuperarse, lo cual es una fracción de lo que se muestra. A pesar de que en dibujo, idealmente todo este calor podrá recuperarse entre las dos, la línea compuesta caliente y la línea compuesta fría. Hay pérdidas al ambiente, ¿no? Entonces el 100% del calor no se va a recuperar. No, como vemos aquí, se instalan estas líneas paralelas, un poco debajo de la línea compuesta fría y un poco encima de la línea compuesta, pero un poco debajo de la línea compuesta caliente y un poco encima de la línea compuesta fría. Y vamos a especificar exactamente por cuánto, ¿no? Entonces, en este espacio entre estas líneas punteadas es donde realmente se puede recuperar calor. La izquierda nos dice driving forces not feasible within each interval. O sea, esto en la vida no es factible. Y acá nos dice heat transfer within temperature intervals now feasible. Esto es más factible en la vida real. The amount that can be recovered depends on the relative slopes of the two curves in the temperature interval. Aquí estamos hablando de intervalos de temperatura entre la línea compuesta caliente y la línea compuesta fría. This problem can be overcome is purely for the purposes of construction. The hot composite curve is shifted to be delta T minimum divided by 2 colder than it is in practice. That the cold composite curve is shifted to be delta T minimum divided by 2 hotter than it is in practice, as shown in figure 1614b. Como lo vemos acá. Y se ha dividido delta T minimum dividido para 2 y delta T mínimo dividido para 2 por debajo de la curva compuesta caliente y por encima de la curva compuesta fría, dejando ese espacio entre estas líneas punteadas nos muestra realmente lo que se puede intercambiar de calor. Usando este parámetro como una referencia, el delta T mínimo dividido para 2. The shifted composite curve now touch at the pinch, como vemos acá. En este punto, cuando se hace la línea punteada, llega un momento que se topan estas dos. Justo ahí se topan. Le llaman shifted composite curve. Entonces, la curva compuesta caliente modificada, por decirlo así. De la curva compuesta fría y la curva compuesta fría modificada por el delta T mínimo dividido para 2 más los valores originales en la curva compuesta. Llega un momento que se topan en este punto que está justamente ahí. Carrying out a heat balance between the shifted composite curves within a shifted temperature interval shows that the heat transfer is feasible throughout each shifted temperature interval. Since hot streams in practice are actually delta T minimum divided by 2 hotter, and cold streams are delta T minimum divided by 2 colder. Within each shifted interval, the hot streams are in reality hotter than the cold streams. It is important to know that shifting the curves vertically does not alter the horizontal overlap between the curves. It therefore does not alter the amount by which the cold composite curve extends beyond the start of the hot composite curve at the hot end of the problem. Also, it does not alter the amount by which the hot composite curve extends beyond the start of the cold composite curve at the cold end. The shift simply remove the problem of ensuring temperature feasibility within temperature intervals. Este proceso, este protocolo de modificar las líneas compuestas calientes y frías se lo hace para asegurar, porque aquí dice the shift simply remove the problem of ensuring temperature feasibility within temperature intervals. En otras palabras, al realizar este ejercicio que se encuentra en la figura 1614b, nos aseguramos que en el espacio remanente el intercambio de calor es factible entre las líneas de proceso caliente y frío, versus que esperar un intercambio como se puede ver aquí, en este intervalo de temperatura, en este cambio perfecto entre la línea caliente compuesta y la línea compuesta fría, no es factible en la vida real. Lo que nos está diciendo. Bien. The shifting technique can be used to develop a strategy to calculate the energy targets without having to construct composite curves. Entonces, esta es la estrategia del algoritmo del problema de la tabla. Número 1, set up shifted temperature intervals from the stream supply and target temperatures by subtracting delta T minimum divided by 2 from the hot streams and adding delta T minimum divided by 2 to the cold streams, as in figure 1614b. Entonces, en esta figura, justamente se hizo de la línea compuesta caliente, se sustrajo delta T mínimo dividido para 2 y quedó esta línea punteada debajo de la línea caliente compuesta. Y a la línea fría compuesta se le sumó delta T mínimo más 2, delta T mínimo dividido para 2, se le sumó esa cantidad y quedó encima, el punto en el cual es La línea modificada caliente y la línea modificada fría se toparon. Muy bien. Número 2. In each shifted temperature interval, calculate a simple energy balance from, tenemos el delta, el cambio en entalpía para cada intervalo, por eso un cambio en entalpía I para cada intervalo de temperatura, la sumatoria de los CP, recuerde CP es MCP, de las líneas frías, cold streams, menos la sumatoria de los CPs H de las líneas calientes. Sumatoria de líneas frías para cada intervalo, menos sumatoria de líneas calientes para cada intervalo. Where delta HI is a heat balance for shifted temperature intervals I and delta TI is a temperature difference across it, que es diferencia de temperatura en ese intervalo. If the cold streams dominate the hot streams in a temperature interval, then the interval has net deficit of heat and delta H is positive. If hot streams dominate cold streams, the interval has a net surplus of heat and delta H is negative. This is consistent with standard thermodynamic convention. For example, for an exothermic reaction, delta H is negative. If no hot utility is used, this is equivalent to constructing the shifted composite curve shown in figure 1615A. Okay, no hot utility, overlap. So it's telling us that the utility target can be determined from the maximum overlap between shifted composite curves. Ustedes recordarán, esto es lo que vimos en el dibujo que se encuentra aquí. Tenemos el delta T mínimo dividido para 2, se modificó la línea compuesta caliente, delta T mínimo dividido para 2 sobre la línea compuesta fría, y se generó esta región de intercambio que es factible. Es lo mismo que se ve expresado justamente aquí. Aquí está el delta T, la diferencia del delta T mínimo entre estos dos. Aquí el punto donde se encuentran las líneas modificadas. Y en este espacio entre las líneas punteadas donde se puede agregar el servicio utilitario caliente, y en este espacio entre las líneas punteadas donde se puede absorber la energía de desecho, el waste energy, usando el utilitario, el servicio utilitario que absorbe energía, que sería el agua de torre, ¿no? El número 3, porque son 3 pasos, el número es setup, shifted temperature intervals, número 2, calculate simple energy balance, y número 3, the overlap in the shifted curves as shown in figure 1615A. Shifted curves 1615A. Correcto, nos dice que heat transfer is infeasible. ¿Dónde es esto? Esta región. Claro. Esta región donde están las líneas punteadas muestran líneas modificadas caliente y fría. Esta región de intercambio, claro, no ha quedado, como usted puede ver, un espacio aquí, como ha quedado aquí, un espacio que representarían un espacio de energía, ¿no? O sea, este diferencial es la cantidad de energía a agregar aquí. En esta región no hay nada que agregar porque está totalmente cerrado aquí. No hay nada que agregar, aquí no hay nada que absorber. Entonces, esta situación así, un gráfico, esta situación, la verdad que no expresaría de una manera clara cómo exactamente agregar energía a este sistema y de cómo absorber energía a este sistema, que está totalmente cerrado. Pero acá está claramente explicado donde el utilitario caliente, que es el vapor saturado, pues este diferencial de H, que esto está sobre la escala de entalpía, este diferencial de energía es lo que debe de aportarse, ¿no?, al proceso sobre el pinch, y este diferencial de energía es lo que debe absorberse del proceso debajo del pinch, ¿no? Eso tiene sentido lógico. At some point, this overlap is a maximum. The maximum overlap is added as a hot utility to correct the overlap. The shifted curves now touch at the pinch as shown in figure 1615B. Since the shifted curves just touch, the actual curves are separated by delta T minimum at this point. Aquí podemos ver que aquí se han topado las líneas modificadas las líneas compuestas calientes y frías, se han topado justamente en el punto del pinch. En el punto del pinch es donde ocurre esa intersección entre las líneas modificadas calientes y frías, justamente aquí. This basic approach can be developed into a formal algorithm known as a problem table algorithm. The algorithm will be explained using the data from figure 16.2, given in table 16.2 for delta T minimum of 10. Aquí tenemos para el proceso que estaba en la figura 16.2, que es este proceso que se encuentra aquí. Se va a listar las líneas de este proceso sencillo y cómo en este proceso se va a usar el algoritmo del problema de la tabla para resolver este problema de este diagrama de flujo de proceso ineficiente, ¿no? Muy bien, volvemos a esto, lo encontramos justamente aquí. First, determine the shifted temperature intervals, que ahora va a ser T estrella, o T, no sé cómo, T asterisco, perdón. Con T asterisco se van a expresar los intervalos modificados de temperatura from actual supply and target temperatures. Hot streams are shifted down in temperature by delta T minimum divided by 2, and cold streams are shifted up by delta T minimum divided by 2 as detailed in table 16.3. Pues aquí podemos ver un cold stream is going from 20 to 180. Now to the right, you see two columns of shifted temperature with T star. T star supply, T star T, target. So the original temperatures were 20 and 180. Now we're going to have delta T minimum divided by 2 plus the cold stream, the supply temperature of the cold stream, and delta T minimum in both cases, delta T minimum divided by 2 plus the supply, the target temperature of the cold stream. So it will be 25 to 185. You will see the opposite on the cold stream. This coming from 250 to 40. So you'll see delta T minimum divided by 2 minus 250. So that's why you see 245. And delta T minimum divided by 2 minus 40, that's why you see 35 for the hot stream. So the cold streams, we have delta T minimum divided by 2 plus the two temperatures, the supply and target temperature. And the hot streams, we have delta T minimum divided by 2 subtracting the different hot temperatures. So you see 195 minus 75. So that will be the way to proceed with the shifted temperature intervals. And now to the right, you have all these shifted temperature intervals. The problem, the stream population is shown in figure 16.16 with a vertical temperature scale. The interval temperature shown in figure 16.16 are set to delta T minimum divided by 2 below the hot stream temperatures and delta T minimum divided by 2 above the cold stream temperatures. Muy bien, aquí vemos como resultado de modificar las temperaturas de las líneas frías y calientes. Tenemos ahora todo este intervalos de temperatura modificados entre la temperatura que se proveyó al proceso y la temperatura objetivo, el target temperature en el proceso. Bien, tenemos todas estas temperaturas modificadas y usted observará que esta escala que se encuentra aquí en esta figura 16.16, usted va a ver la escala de las temperaturas modificadas. Aquí tenemos desde la menor a la mayor, vamos a listar 25, 35, 75, 145, 195, perdón, 145, 185, 195, 235. Estas 8 diferentes temperaturas las va a usted ver reflejadas aquí. 25, 35, 75, 145, 185, 195, 235, 245. Eso se encuentra reflejado, queriendo decir que vamos a graficar las líneas frías y las líneas calientes utilizando estos intervalos. Recuerde, este intervalo obedece exactamente a las temperaturas modificadas, dividiendo las líneas calientes, delta T mínimo, el mínimo dividido para 2, más las dos temperaturas frías, o delta T mínimo dividido para 2 más menos las líneas calientes y más las líneas frías. Así funciona la cosa. Es menos, en el caso de las líneas calientes, se resta ese valor o se agrega ese valor a las líneas frías y así se procede para obtener las temperaturas, le dice cambiadas en inglés, shifted, no sé cómo decir, pero le llamaría modificadas. Son las temperaturas modificadas de las dos columnas de la derecha. Con esas temperaturas modificadas se hace el gráfico que se encuentra en la figura 16 y se coloca pues punteadas las líneas que representa cada intervalo. Observe usted que no es un intervalo como hecho en un gráfico que está perfectamente separadas a escala las diferencias de temperatura, porque usted tiene aquí 10 grados, aquí tiene 40 grados, aquí tiene 70 grados, aquí tiene 40 grados, aquí tiene 10 grados, eh, aquí tiene 40 grados y 10 grados. Entonces esto no obedece una escala. Y así lo tenemos que graficar sin obedecer específicamente una escala de temperatura, sino simplemente colocando este intervalo así, de manera vertical, del más caliente al más frío. Luego procedemos a graficar las líneas, por decir. La primera es un cold stream y va de 25 a 185, es la que ve. Línea 1 va de 25 a 185 y colocamos al lado de la línea la temperatura real que calentó de 20 a 180. Y usted puede colocar en las líneas sombreadas, las líneas entrecortadas, la temperatura real. Como es una línea fría, ya sabe que es delta T mínimo dividido para 2, quiere decir que la temperatura real fue 5 grados menos en cada intervalo de estos de aquí. Fue 30, 70, 140 y 180 en lugar de estas temperaturas que se muestran a la izquierda. Claro que en una tarea, en un examen, no tiene que estar detallando todas estas temperaturas, pero se lo expresa aquí para que usted quizá comprenda, ¿no? Eh, en este intervalo, por decir, en las cuales hay un overlap, como se diría, entre la caliente y la fría, puede haber un intercambio de calor. Porque en realidad la línea caliente tiene unos grados encima de la línea fría y aquí vemos el delta T mínimo de 10, de 10, de 10, de 10, ¿no? Es constante entre la línea caliente y la fría. Entonces, para efecto de eso es que se ha colocado todas estas temperaturas. Pero basta con llenar esto, las líneas sombradas y colocar en el gráfico eh, donde corresponde cada línea para efecto de tarea o para efecto de examen. Lo demás se ha colocado para que el lector, en este caso el lector del libro, pues pueda ver claramente el delta T mínimo de 10 entre las líneas calientes y las frías en el intercambio, en el intervalo de temperatura donde coinciden, ¿no? Como en este caso coinciden, como aquí coinciden el intervalo de temperatura, ¿no? ¿Qué más vemos acá? The interval temperatures shown in figure 1616 are set to delta T minimum divided to, bueno, esto ya lo vimos. Veamos para la línea 2, esto va de 250 a 240 en la vida real o 245 y 35 modificado. Aquí vemos 245, la línea 2 va a 235. La línea 3 va de 145 a 235, la línea 3 va de 145 a 235 y la línea 4 va de 195 a 75, como vemos aquí, 195 a 75. Entonces, se grafica la población de líneas de proceso, un gráfico de población de líneas de proceso. Vemos aquí el intervalo 25 a 185 que representa 20 a 180 en la vida real. Dice stream 1 with shifted temperature range. Ok, aquí tenemos el proceso en la figura 16.2, las 4 líneas de proceso. Next, a heat balance is carried out within each shifted temperature interval according to equation 16.1. Recordemos el intercambio de calor. El diferencial de entalpía en cada intervalo de temperatura, la sumatoria de las líneas frías menos la sumatoria de las líneas calientes por el delta T de ese intervalo. The results is given in figure 16.17, lo vamos a ver acá, in which some of the shifted intervals are seen to have a surplus of heat and some have a deficit. The heat balance within each shifted interval allows maximum heat recovery within each interval. However, recovery must also be allowed between intervals. Vamos a verlo. Aquí tenemos esta es la operación que va a realizarse. delta T por la sumatoria de los CP de las líneas frías, o menos la sumatoria de CP de las líneas calientes, hot. Esto nos va a dar el cambio de entalpía en cada intervalo. Los intervalos están dados, como vimos acá en el dibujo anterior. Los intervalos están dados por las temperaturas modificadas en las líneas frías o calientes. Estos son los intervalos de temperatura. Y en estos intervalos vamos a calcular el delta H que pertenece a cada intervalo en particular. Delta H de cada uno de ellos dentro del delta T de cada uno de estos intervalos. Muy bien. Para el primero, tenemos un delta T entre 245 y 235 de 10 grados, donde la sumatoria, ¿cuál sería la sumatoria? Sería la sumatoria de las líneas frías. Aquí no hay ninguna línea fría que está aumentando de temperatura, sino menos, dice la línea caliente. Tenemos una línea caliente de 0.15 de CP, sería menos 0.15 y es lo que usted observa aquí. Por el intervalo de 10 grados se hace menos 1.5 delta H, que es lo que usted observa aquí. 10 grados por menos 0.15 es 1.5 megavatios. Seguimos con el siguiente, y está en rojo porque está entregando energía. Azul porque está requiriendo energía o hay un déficit. Rojo porque está entregando energía o hay un surplus de energía. Es sencillo. Siguiente intervalo. Aquí tenemos las líneas, una vez más, la sumatoria de las líneas frías menos la sumatoria de las líneas calientes. En este intervalo, entre 195 y 235, tenemos solo una línea fría, que es la de 0.3 de CP, y eso habrá que restar de la única línea caliente en ese intervalo, que es la de 0.15, y nos queda 0.15 positivo. Línea fría, 0.3, menos línea caliente, 0.15, y nos queda un saldo de esa diferencia de sumatorias positivo. Como el intervalo es de 40, 195, 235, es de 40, por 0.15, que es este operación de este balance de energía, 0.15 que nos arrojó en ese intervalo, ahora nos arroja un intervalo de 6 megavatios positivos, representa un déficit de energía en ese intervalo. Siguiente. Tenemos entre 185 y 195, 10 grados de diferencia de temperatura. Nos toca hacer el balance entre las líneas de proceso frías y calientes. Tenemos una línea fría, 0.3, y dos líneas calientes, la de 0.15 y la de 0.25, que suman 0.4. 0.3 menos 0.4 es 0.1. Por 10 del intervalo de temperatura nos da menos 1 megawatt, que representa un exceso de energía o un surplus. Siguiente. En este intervalo entre 145 y 185 tenemos 40 grados de diferencia de temperatura. Tenemos dos líneas frías, 0.3 y 0.2 que suman 0.5, y dos líneas calientes, 0.25 y 0.15 suman 0.4. 0.5 de estas dos menos 0.4 de estas dos representa 0.1 por 40 es 4. Entonces queda un déficit de 4 megavatios en este intervalo. Siguiente. El diferencial entre 75 y 145 es de 70 grados. Tenemos una sola línea fría de 0.2 y tenemos dos líneas calientes, la de 0.15 y la de 0.25 que es 0.4. 0.2 menos 0.4 es menos 0.2. Por 70 es menos 14 y tenemos un exceso de energía de menos 14 megavatios. Siguiente. En este intervalo tenemos un delta T de 40 y tenemos no hay líneas, perdón, si hay una línea fría de 0.2 y tenemos una línea caliente de 0.15. 0.2 menos 0.15 es 0.05, que es lo que se refleja ahí por 40, da 2.0 y como está en positivo es un déficit de energía. Finalmente, tenemos en el último intervalo de 25 a 35, 10 grados centígrados. Tenemos una línea fría y no hay líneas calientes, sería 0.2 positivo por 10 es 2. Y una vez más tenemos un déficit de 2 megawatts de energía. Así se construye este tipo de diagrama, se llama Temperature Interval Heat Balance. Este tipo de diagramas son Temperature Interval Heat Balance, porque está haciendo un balance energético, está determinando los delta H en cada intervalo, un balance energético en los intervalos de temperatura que se encuentran según la temperatura modificada de líneas calientes y frías. Entonces es un Temperature interval heat balance, balance energético de intervalos de temperatura. Muy bien, veamos esto y con esto creo terminamos las pocas diapositivas que nos quedan. Creo que alcanzamos a hacer este ejercicio. Now, cascade any surplus heat down the temperature scale from interval to interval. Vamos a hacer una cascada de temperaturas, de la temperatura más alta hasta la menor, a manera de cascada. Y así funciona esta tabla. This is possible because any excess heat available from the hot streams in an interval is hot enough to supply a deficit in the cold streams in the next interval down. Figure 1618, tenemos 1618, shows the cascade for the problem. First, assume no heat is supplied to the first interval from hot utility, figure 1618. Entonces aquí podemos ver cómo en la tabla de la izquierda se ha ubicado, usted recordará, todos estos diferentes balances energéticos que se obtuvieron para cada intervalo se van a trasladar a la tabla, exactamente como tal, junto con su respectivo intervalo de temperatura. Entonces usted podrá observar, inicia el primer intervalo entre 2.45 y 2.35 con el delta H obtenido de la tabla. Delta H fue menos 1.5 y el intervalo fue 2.45, 2.35, el primer intervalo. El segundo fue de 2.35 a 195 con un delta H de 6, que usted lo puede ver aquí. 2.35, 195 con un delta H de 6. Así se construye toda la tabla. De tal manera que encima del intervalo, el último intervalo, ¿no? El intervalo, la temperatura modificada caliente, encima de esto va el hot utility, donde tenemos que agregar calor, y debajo del último intervalo de temperatura va el cold utility, donde se absorbe el rechazo de calor. Básicamente así funciona la tabla. Entonces, podemos observar en la tabla de la izquierda, son dos tablas exactamente iguales. Lo que modifica son estas lecturas, el procedimiento, digamos. En la primera tabla, la de la izquierda, usted va a agregar 0 megavatios como servicio utilitario de vapor saturado, va a agregar 0, no va a agregar nada de energía. Y va a ser una cascada hasta el final. ¿Cómo la hacemos? Bueno, hacemos 0 menos 1.5. Recuerde, vamos haciendo cascada hacia abajo, así que vamos restando. Y como vamos restando, la resta de una resta se vuelve positiva. 0 menos 1.5 se nos hace 1.5. Ese 1.5 positivo menos 6 se nos hace menos 4.5. Menos 4.5 más 1 se hace menos 3.5. Menos 3.5 menos 4 se hace menos 7.5. Menos 7.5 más 14 se hacen 6.5. 6.5 menos 2 se hacen 4.5. 4.5 menos 2 se hacen 2.5. Aquí hay un error, ¿no? 2.5. Muy bien. ¿Qué notamos aquí? Que el que tenga, observamos, en cuanto el que tenga con signo negativo, la magnitud mayor. Y de estos intervalos que vemos aquí, el que tiene la magnitud mayor es justamente el que se encuentra aquí. Y ese es el valor que usamos para la tabla de la derecha como input, como ingreso de energía. Vamos a ingresar, ahora en positivo, 7,5 megavatios en la tabla de la derecha. Y ese vamos a hacer una cascada justamente hacia abajo, del mismo modo que hicimos la cascada de energía en la tabla de la izquierda. 7.5 megavatios, lo que se ve aquí. Y 7.5 megavatios más 1.5 se hacen 9, menos 6 se hacen 3, más 1 se hacen 4, menos 4 se hace 0. Este punto es el punto pinch, que también en el mismo punto se observa a la izquierda donde estaba la magnitud mayor de energía. Coincide. Este punto en la tabla a la derecha, el punto 0, es donde se encuentra el pinch y donde está el valor donde se topan las curvas modificadas caliente, curva compuesta caliente y curva compuesta fría, se topan en este punto de aquí donde usted puede ver que no es ni 140 ni 150, sino que es justamente el punto modificado de ambas curvas, que es el 145. Y continúa la cascada. 0 más 14 es 14. 14 menos 2 es 12 y 12 menos 2 es 10. De tal modo que el 7.5 que partió de la mayor magnitud menor de la tabla de la izquierda es la cantidad de energía a agregar a manera de vapor saturado al inicio del proceso, la parte del proceso que actúa como sink, ¿no? Heat sink se le dice, como, no sé cómo expresar. Y la parte del proceso que está rechazando calor al final son los 10 megavatios en donde se va a bombear agua de torre para absorber y el proceso está actuando como fuente de energía, como heat source. Van a ser absorbidos por el agua de torre en esta magnitud de energía, 10 megavatios. Entonces, en resumen, aquí podemos ver el pinch point. Entonces, el hot pinch vendría a ser 145 más delta T mínimo dividido para 2, que es 150, 5, más 145, 150, y el cold pinch sería 145 menos delta T mínimo dividido para 2, que son 5, se hacen 140. Aquí está el intervalo. El punto modificado de las dos líneas se topa justamente en 145. Esto de acá, como ya llegamos al tiempo, no quiero tomarle más tiempo, lo podemos continuar mediante el día jueves. Esta discusión que está bastante interesante y de paso, pues les agradezco su paciencia en esta clase. Es importante, el día jueves, Dios mediante, continuamos. El día viernes tienen tarea y esperamos enviar la tarea número 4 el día viernes, que justamente va a tratar de este tema. Entonces esperamos que sea interesante y el tema del examen final también. Por lo demás, jóvenes, muchas gracias. Les deseo una excelente noche. Gracias por su tiempo y nos vemos, Dios mediante, el día jueves. Que tengan una excelente noche, cada uno de ustedes.
Gracias,
Gracias,
profe.
jóvenes.
Gracias, profe.
Gracias. Muchas gracias.
Gracias.